So as I was talking about, the lowest molecular weight will come out from the top. The highest molecular weights will be at the bottom, and the residue, this is where the tars are down here. Okay, so you can see as it progresses, you get fuel oil, diesel, kerosene, naphtha, and gasoline. Gasoline is about C7, C8. That's why you usually look at it in terms of octane ratings. Okay, so the lower part here is large molecules, high boiling points. They're not very volatile. They don't flow very easily, as you know how tar is down here. And then up here you have the very low boiling points, very volatile, flow easily, ignite easier. Now, as a matter of fact, some of these right here are refinery gas, and they just burn those as soon as they come out. That many times they don't even try to recover them. So now the reactions that you have for these hydrocarbons is that these bonds right here will react with chlorine or bromine or one of those, and either heat or light will cause them to replace one of the hydrogen atoms with a chlorine atom. Okay, and that forms this, for example, chloroethane with hydrochloric acid. And this is as a gas, and this is also as a gas. And if you have a much higher concentration of this and varying conditions, you can substitute other ones of these until you actually can get more substituents on here. And this is one of the other ways of looking at these is you have the possibility, as we saw when we were doing our structures, of having double bonds, right? And this is ethene, this is propene, this is 1-butene. Okay, on these it doesn't matter. I mean, this double bond could be here or here, but it's going to be between the first and the second from whichever way you count. Once you get to 4 or more, there's other places where the bond can be. And so you start counting from the one that would give the smallest number. Instead of butane, it becomes butene. Okay? And this right here, if you have all of these unsaturated with a catalyst, usually it's a Ziegler catalyst, but I wrote a paper on that quite a while ago, many years ago, and learned about the intricacies of this. But anyway, with a catalyst, under certain conditions, all of these different ethylene molecules can then be converted to polyethylene, right? That's where polyethylene comes from. It's from all these different ones. This bond breaks, okay, and links to here. This bond breaks and links to there, and it just keeps on going, and you have a whole variety of different molecular weights, and by controlling the processes, you can get a fairly narrow distribution of those, so you can have quite good properties for your different polymers. We'll talk more about that later. This right here is just something about for the different plastic bags or other things that you see. You might want to look for what they have on them, because that will tell you what it was made from, and it also gives you ways so that you can recover those if you want to ever recycle. So this is ethene or ethylene. This is propene, or the more common words for these are ethylene and propylene, right? Once you get beyond the initial smaller ones, then it becomes necessary to use the formal word and to also say where the bond is. This is 1-butene. This is 2-butene. Okay. This right here would be 1-butene. And what you'll notice here is that with this, you can have two different isomers of this for the 2-butene. If that bond is here, you can have it like this, where these two are opposite each other, or this, where they're on the same side. Or you can be looking at it, whether it's the hydrogens or the methyl groups. You look at it in terms of whether it's a cis, which has a very different configuration than this. And these also react differently. Okay, so these isomers are distinctly different around double bonds. As a matter of fact, to that point, when you looked at some of the drugs that have been on the market, getting a pure isomer can mean the difference between no birth defects or having birth defects. That was exactly the problem with one of the drugs that came out that was used for calming mother's nerves, but one impurity caused deformities in the child that was born, whereas the other one would have been perfectly fine. Had they been able to isolate the two different isomers, they would have been able to do that. Subsequently, that same molecule has been isolated so that they have a method for getting just one of the isomers, and that is very much in use today for some other uses. So structures are very important. Now, the ethene bond, this double bond, has a lot more energy. So with this, it's a lot easier to put chlorine molecules here. So instead of replacing just one hydrogen, what you're going to do is you're going to actually break this bond and add a chlorine to each one of these carbons. So from this, you get 1,2-dichloroethane, right? So this is a very common reaction when you want to halogenate or chlorinate or iodate or brominate a molecule. This is the type of reaction that you do. You go with something with a double bond, and at that double bond, you will replace it with two of those different halogen elements. So here, what you will do is something like this. The double bond is here. So this would be CH3, CHCl2 here, CHCl2 here, CH2, CH3. And so what you're going to end up with here is going to be 2,3-dichloro, 1, 2, 3, 4, 5, pentane. So it'll be 2,3-dichloropentane for that material, right? That's exactly what you end up with. Here you have 1, 2, 3, 4, 5, 6, right? And it's going to be 3 from either side, isn't it? So this is going to be 3,4-dichlorohexane, right? Now, when you have a triple bond, it has even more energy. These are called, these end in YNE. So you notice that with a single bond, it's an ANE. Double bond, it's ENE. And 3 is YNE. And this is acetylene, right? Or ethene is the formal scientific name. Acetylene is a more common name that we use. And this right here, you count from to get the smallest number. To anytime you have 4 or more to get exactly what these are. And so this is going to be 2, and this is going to be 1, 2, 3, 4, and so that's going to be butane, right? Butane, B-U-T-Y-N-E, 2-butane. Now you have a double bond over here and a triple bond over here. So what you're going to do is you're going to start counting from where the more complex one is, but the name of it comes from this, okay? So it's 1, 2, 3, 4, 5. So this is going to be so it's going to be 3-pentene 1-ine. Anytime you have a triple bond and a double bond, they're called something else. They're called an alkenine, A-L-K-E-N-Y-N-E. And so that's why for that 1, you start with this number right here. And so it will be 3-pentene, P-E-N-T-E-N, then a hyphen 1 for this one right here, Y-N-E. So a pentene 1-ine. 3-pentene 1-ine. Okay? So, as I mentioned, these are very, very reactive. and release a lot of energy, so that if you put twice the bromines in there, this is going to be 1,1,2,2 tetrabromoethane, right? So you have where each one of these 4 bromines are located. There's 4 of them on there, so that's why it's a tetra. We talked before as well, there's other double bonds you can have as well, but it's ring structures, and these resonate back and forth between these two. And this is a condensed version of that, and so that you can actually have something like this with substitutes off from it. With one methyl group on that benzene ring, it's given the name toluene. If it has 2 methyl groups on there, it's called xylene. And if it's a CH double bond CH2 or an ethylene group up here, it's called styrene. Okay? And then if what you do is from that particular one, you give it different names. For example, here, if you've got something in this position with a chlorine group, and this is 2 ways to represent it, this would be toluene if not for here. But this is in this position over here. If something is right next to it, it is called ortho. If it is 2 over, it is called meta. If it is called directly opposite, it's called para. And these are abbreviated as an O, a M, or a P. So this right here would be meta-chlorotoluene, right? Meta-chlorotoluene. And so this right here is metachlorotoluene. This right here is parachlorotoluene because it's located in this position over here. Parachlorotoluene. Here, when you have other substituents on here, this would be 1,2-dibromobenzene. This would be 1,3-dibromobenzene, and this would be 1,4-dibromobenzene. Or you could call it, it's best to use it just that way. Now let's talk about alcohols and ethers, okay? We're going to describe the properties and structure of alcohols, structure and properties of ethers, and I want you to be able to name and draw the structures of these. I mean, that's the whole purpose of this part. Now, what happens is we're all very familiar with a fermentation process. A fermentation process takes glucose or sugar from some sort, and it can be grapes or corn or whatever, or potatoes even. And with the addition of certain types of yeast, it will ferment to give ethanol and carbon dioxide. And depending upon the yeast and the source of that material, you can get different concentrations of this ethanol. And then you can further refine it by distillation to get a very high concentration. But all the time when you are doing this, you are taking glucose with the yeast to create an alcohol. Now, there are other alcohols that you can prepare as well. Remember, we have those double bonds that are very, very reactive. And if you take an acid with those and add water to it, you can break that double bond so you get a hydrogen off of one of these and a hydroxide off of the other so that it becomes an OH group. Okay, OH. Now this right here is not an ionic bond. This is a covalent bond, and this hydrogen is covalently attached to here. So this is a fairly stable molecule. This oxygen and hydrogen are not going to be given off unless you really do some serious reacting to this. But this is the way, and another way, in which alcohols can be formed.